All right, so this video clip from Hidden Figures references Euler's method. It's super old. Actually, what she says at the beginning, where she says there's no mathematical model for that, that's why they couldn't do it like with separation of variables. They couldn't fit it to a math model in order to solve it. So Euler's is another one of those methods where you get approximations, but not exactly because you can't do it exactly. So it's kind of cool.
The problem is when the capsule moves from an elliptical orbit to a parabolic orbit.
Just a minute. Did I press play on that video? I did. It's recording. Okay. I was talking.
Because we can calculate launch and landing, but without this conversion, the capsule stays in orbit. We can't bring it back home.
Maybe we've been thinking about this all wrong.
How's that?
Maybe it's not new math at all.
It could be old math. Something that looks at the problem numerically and not theoretically. Math is always dependable.
For you, it is.
Euler's method.
Euler's method.
Yes.
But that's ancient.
But it works. It works numerically.
That's it.
Let's type it up.
Did you kind of see how ugly that number was? Well, these are always no calculator on the AP exam because you can write a calculator program for it pretty easily. I've actually in past given extra credit for kids who know how to program to write a calculator program for it. It's not very hard. And so it's always no calculator. So the only issue that some of you might have with it is that because you're doing numerical arithmetic, some of you, you're going to make decimal point errors and that type of stuff, and you won't have a calculator, so you're going to be dying to take out your calculator to do 0.92 times 0.7, and you can't. So that's the only problem with it is you would have to do it by hand like they did. Now they have computers where if you wanted to do Euler's method, you just plug the numbers into a computer and it'll do it. So it is old, and it's since been computerized, so it's actually not so ugly, and it's not ugly in and of itself. They keep the numbers pretty reasonable for AP, but like you saw the real world one, it got really ugly numerically. So we're going to actually hop on here, and I'm going to talk about what Euler's does, because it kind of helps if it's easy to do, but kind of understanding what it's doing is kind of interesting. So in your notes, you're going to have, like we've done with separation of variables, you're going to have, in this case, I have a rate of change that's been calculated. It could be a speed or a velocity in the real world or something, but it's some rate of change. You do need to have what we call an initial condition for this. You do at least need to know one point. I think you kind of saw that orbital thing. It kind of had one point and a vector drawn off of it. You do need to know that. So you do need to have what I call an initial condition, or where to start the problem. Again, in the real world, that's probably really ugly coordinates of some sort. But for us, so what you're going to use that to do is estimate what happens later. Like, we're going to estimate, well, what's going to happen later? What will my numerical value be later? So it's going to tell you to hop on at a specific point. So graphically, this is what's happening. You can't see the function, correct? You cannot see it. Pretend it was going like this, and you hopped on right here. In Calc 1, or AB, you did tangent line approximations. And we said they're okay, but you have to stay pretty close, correct? What Euler's does, it stays on the tangent line only for a while, and then it readjusts the slope. So I kind of like it to call it like walking a tightrope. So yeah, I will walk along this tangent line for a little while, but then I'm going to stop and readjust the slope because it's starting to curve. Does that make sense? When you stop, or in the real world, it'd be like a time unit, but for you guys, it's an x unit. It's called the step size. So we'll call that delta x in like our math model. If you're not told what delta x is, you'll be able to figure it out. So it'll be an initial point of 2, and maybe you're going to estimate 6, and maybe it'll say with 8 step sizes, or 8 steps. We'll be going from 2 to 6. 6 is 4. So I'm going to have to go by halves. Does that, you know what I mean? Sometimes you're going to have to figure that out, but usually step size is really easy. The smaller the step size, guess what happens? The more accurate it is. So this one's not very accurate because I'm taking a full step of 1 just to get to 4. I mean, if I did it by 0.1, I'd keep readjusting, and it almost looked like it matched, correct? So a lot of times things that look like they have curvature, like you ever, like on a roller coaster or guardrails on the highway, don't they look like they're curved? They're not. They're straight, but they're following it. That's kind of what you're doing. They're not curved pieces of wood making the guardrail, but when you look at it, it looks curved. So what you're going to do is you just hop on right here, and you're just going to calculate the slope. So if I were to do that, I'm just going to show you, and then I'll give you kind of a shorter. I'm going to start this. I'm going to say, well, I have to start at 0, 1, and it tells me right here my slope is equal to the y value, correct? So my slope, I'm just going to use point slope from Algebra 2 just to demonstrate this. So the tangent line I'm going to draw here would be the one where y minus the y I know is equal to the slope, which is 1 times x minus the x I know. Correct? Are we good? Which would be that that's x minus 0. My y would equal x plus 1. Does that make sense? So at first, I hopped on here at 0, 1. And at 0, 1, I had a slope of 1. And I'm going to hang out there with a slope of 1 for a little bit. Okay? But then at 2, because it's a step, or at 1, I'm going to stop. So instead of heading straight that way, like I would in Calc 1, I'm going to stop right here, and I'm going to readjust it. Does that make sense? So I'm going to stop right there, and I'll be at this new point. I'll have gone 1 to the right, because it says to do a step size of 1. Right? So it's going to go 1, and then 2, and then 3, and then 4. Does that make sense? I keep doing, it's called iterations. I keep doing it over and over again. But my y value there would be my old x, right, plus 1. And then you keep doing it, and you keep doing it. And I'm not going to do it on here because it's kind of awkward. I'm going to show it to you actually tabularly. All right? So we're not going to continue with that. I'm going to show you kind of the makings of it. First of all, you always have what I call a start. And what you're going to do is you're going to put it right here. Well, it was 0, 1 on that one, correct? Then what you're going to do is you're going to hop on basically at that point, and you're going to walk along that with a particular given slope. They will tell you. Correct? We're good so far? And for mine, that first slope was 1 because it said dy dx equals y. So I said it was 1. Okay? So you start here. You start making a slope of 1, right? Then they're going to tell you how long to do that, which is called delta x. And this one, my delta x was what? 1. So I'm going to call that, well, you need to kind of step to the right. And then you have to figure out, well, how far up do I go? This is where, take a look. What's another word for dy dx? Slope, correct? Haven't you learned that slope is change in y over change in x? Wouldn't you agree? You've done that a ton, right? So wouldn't the change in y equal the slope times the change in x? Agreed? So to get your delta y, go like this, you're always just going to multiply these. It's the slope formula. Slope is change in y over change in x. So if I know my slope and my change in x, that's change. You're just going to multiply those two. So on this one, it would be 1. What I'm saying is walk 1 to the right and 1 up. Does that make sense? Okay, so you're on a tightrope with a slope of 1. Then you're going to go 1 to the right and 1 up, and you're going to be at your what I call my new point. So take a look. If I was at 0 and I went 1 to the right, I'm at 1. But I was 1 up, and then I went 1 up, so I'm at 2. Does that make sense? So I walked with a slope of 1 till I got to that point, and then I stopped and I readjust my slopes. Otherwise, I'd be continuing on this straight line and they're going to differ, correct? So now watch. Now what is my new slope? 2. I'm going to go steeper. So you see how I'm following the curve now? I was heading out at 1, I stopped, and now I'm going steeper. Do you kind of get what's happening? So over here, my delta x is still 1. Those are always the same. You always take equal step sizes. My delta y, according to what I've said, is going to be what? 2. Yeah, it's always the product of these two. You will walk with a slope of 2 till you get to a new point. Then you're going to stop and adjust. So my new point now is, well, I was at 1 and I went 1 to the right, but I went 2 up. So where am I? 4. Does that make sense? And then you see how this could be a really easily made computer program? Very easy for those of you who understand computer programming, which is why it's always no calculator, all right? Because now that we have computers, it will run through this. Guess what you'd have to enter into your computer? Start, rate of change, step size. Correct? And probably the interval, I suppose. And it would calculate everything. But again, now I'm going to stop, and I'm going to adjust my slope. What am I going to make it now? 4. Yeah, it's the y value. So I'm now going steeper. So if I were to go back up there, which I will in just a second, delta y would be what? 4. It's always the product of those two. And then over here, I'd be at 3, 8. Are we good? And then I'd have a new slope. I go even steeper. So back up to this picture. 1, 2, 2, 4, 3, 8. I'm going to go up here. I would have been following along 1, 2, and then 2, 4. 1, 2, 3, 4. I'd have followed kind of that. And then 3, 8, I would have gone up here. And the next one, do you see how that's resembling kind of a curve? Sort of. Do you agree with me? Now watch if I extend it this way and extend it that way. What function does that kind of look like? E to the x. Isn't e to the x the only function whose derivative is itself? Right? Or I could separate that. Let's go do it. 1 over y dy. I love it when people go, oh. I could separate this one and do it exactly. They wouldn't have had to do Euler's method historically on that, because you remember she said we have no math model, right? I got one here. I'm going to separate. I get natural log of y is equal what? X plus c. Agreed? You don't have to write this down. Just watch. I exponentiate. I get y equals c e to the x. Are you okay with what I just did there? Are we good? And what point is it supposed to go through? 0, 1. Right? So when I put in a 0, 1 has to come out, so c has to be 1. That's the function y equals e to the x. It looks kind of good, right? We could not have done that in AB, because I would have said, hey guys, what function does this look like? And you'd be like, a line? No, that's not the one I'm thinking of. But you couldn't cause it to turn. So that's what we're going to do. So on the next page, go take a look at what it says. It's got some of the history of it. And it says, sometimes we can't solve them, and slope fields are good for getting a graphical picture. And it says the problem with this approach, the slope field one, is it's only really good for getting trends and solutions. You know how I say squint? That's like what's trending on your paper? Like what squint? But maybe you want to see more how it behaves. So then we can kind of go, and I told you it's kind of like walking the tightrope. This is Leonard Euler. But let's just talk about the machinery you need to run Euler's method. You need to be told a couple things. What are they? Initial spot. You need to be able to hop on somewhere. So we call that an initial condition. In a formula, if we were to write one, usually if you were to look up Euler's in a textbook, you're going to see some x sub 0, y sub 0, which is kind of where am I starting. What else will you need? The rate of change, correct? You will need to know dy dx. If you could separate it, you wouldn't need to do this, correct? But we've got to keep it kind of on the simple end because we can't use calculators. You need to be told that, and you need to have enough information for one other thing, the step size. Okay? And we're gonna call that delta x. You're gonna talk here, when I talk about delta math, I'll say take a step forward or a step backwards if delta is negative. That's me stepping, right? The delta y we calculate. Do you remember how we calculate it? Multiply those two, correct? So the step size underneath it, write a little bullet. You will either be told it, like it'll say with a step size of 0.1, or they'll give you how many steps you need to take. Like it'll say go from 4 to -2 with 4 steps. And you're going to have to think about, well, how am I going to space that out? All right, so you might be told explicitly, let's write this. That's your favorite. If they just say, we have a step size of 0.3. Oh, that's nice. I get to use that. And that means you do 0.3 every time. So on your whole table, 0.3 runs down it. Or you're told how many steps to take. So let's talk about that. If they give you an initial condition of, let's say, 2, and it doesn't matter where you are. Let's say you're at 2, 1 for your initial condition, and they tell you you want to estimate f of 0 using, and I'll tell you how many steps, 4 steps. Basically what you have to think is, how do I get from 2 to 0? How many units is that? But it's not 2, because that would take me 2 to the 4, right? It's -2, right? So I need to span -2, so you kind of have to look, all right, over 4 steps. So what would my step size be? -0.5. So sometimes you have to think that out, but usually it's pretty straightforward. So again, this is what I have you guys do right here. There's 2 ways you can teach this. I've done it differently. I kind of like vacillate between the 2. I gear myself towards this one because kids remember it better. You know what I mean? It's easier to remember it if you lay it out on the table. The problem is if you ever Google for help, it's usually done just iterations of point slope form over and over and over again, like I started doing on that other one, and it gets messy. All right, so here we go. I'm going to go down this one. I'm going to change this to a squaring just so our arithmetic doesn't get too nasty. We're going to make a table, and the mechanics that we need for it to work are an initial point. Where am I going to hop on this unknown function? It says y of 0 equals 1. So I start right here, and I go point. And I'm going to start at 0, 1. Let's see if you already don't have to look at that table. Think of what you're doing. That's why the table's easy to remember. You're going to hop on at this point, and you're going to walk for a while with a certain what? Slope. So what goes next? dy dx. Okay? How long are you going to do that? Well, whatever my step size is. I'll need to step to the right or to the left, right? Any correct? And then I'll have to move up. So this table, it makes sense. Hop on, calculate your slope, then readjust, move to the right, move up, or left and down, whatever, and then you'll be at a new point. Then what do? Start all over again. So it's really quite simple. Here's what I'm going to do. It tells me right here that my slopes, my dy dx's, are the square of my x value, so I'm just going to write it up there. So basically, I'm supposed to start at 0, 1, and go with the slope of 0. How am I walking? I'm just walking straight across for a bit, correct? Then I'm going to stop and adjust. Okay? I'm going to adjust that. I have to figure out my delta x. What does it say the step size is? 0.3. So I'm going to do that for 3/10 of, let's say, a mile. All right? But I also have to move up. So, like, I'm going to go over 0.3, up, plot a new point. How far up am I going to go? 0. Yeah. So on this one, my new point will be, where was I? At 0, but I went 0.3 to the right. My y's were at 1, and I didn't move at all. Back over to here, 0.3, 1. We're going to hop on u and walk with the slope for a while. Of what? X squared. So what do I put here? 0.3 times 0.3. Is it 0.9? No. It's point what? That's what I said is going to get you those. There's little decimally fraction issues in here, but isn't the theory of it kind of cool? Like, why stay on a tangent line? Why not stop and adjust it? Makes sense, right? Should have done it in AB. It's just not in that curriculum. All right? So there's really nothing Calc 2-ish about this, I don't think. I don't know why it's considered a high-level topic. But anyway, how far am I going to scoot? Always delta 3. But now this is going to change. Now I'm going to start moving up a little bit. What do I do with these two things? We multiply because the slope is change in y over change in x. So change in y would be the product of the two. But now you have to multiply those without a calculator. So, do we know how to multiply decimals? It would be 27, but there's how many decimal places? 1, 2, fill the hole with a 0. Right? So, what is this? 0.027. Yeah, I'm not teaching how to multiply decimals. You can Google it if you need to. All right. So now where am I going to be? 0.6 and where? 1.027 because I was at 1 and I'm moving up that much. Now what do? I go back over here and I go to 0.6 and I do my 1.027. Okay? And now I will calculate my dy dx. Again, I need to square the x. What is it? 0.6 times 0.6. It'd be a 36, but there's 1, 2 decimal places. I knew this happens every year. No. You do it as if the decimals aren't there, and then you scoot to the left. 1, 2. Boom, boom. Why was there a 0 here? Because when I do it, I get a 9, but there's 2 decimal places. 1, 2. So, see what happens every year. It's my least favorite part of teaching this lesson. Kids are going, how do I have decimals? All right, so this would be a 0.36. What's this? What is this? Always. Step sizes are equal steps. Now you have to multiply these without a calculator, kids. So you're going to say, well, you're going to ignore the decimal places. 8 carry the 1. And if you say, I'll just take out my calculator, I'll never know, but you're going to get to a test, and then you're going to not have it because this isn't calculator active. How many decimal places am I going to move? 1, 2, 3 to the left. So that one's a 0.108. Now where am I? Where they wanted me to walk to. I was supposed to estimate where I would be when x is 0.9. I now just need to add this to what? To my old point. Yeah, it's my new y value. So again, line your decimal places up. 5, 1, 3, 1, decimal 1. What? I'm adding decimals. It's not earth-shattering. So the answer to this question is the y value at 0.9. It kind of depends what y is measuring. I don't know. These are just generic. But whatever the y's we're doing, I'm estimating that the output is going to be about 1.135. Now this is where it gets. You'll see the accurateness of that. This is accurate. And I can make it super accurate. But let's go see how accurate it is. Because on the next page, it says, determine the error. Error analysis is going to be huge for us second semester. This semester we don't have much of it. But an error is its actual value. Like, what is it? You might say, I don't know. We do, actually. Minus our approximation, correct? And our approximation was 1.135, is that right? So I need to figure out what is it actually there. Which if I could do, I would never do this. So it's kind of circular reasoning. But I approximated, and now I'm going to go say I'm going to do it exactly. But you usually use this method when you can't do it exactly. Does that make sense? But my original function or derivative was dy dx equals x squared. Right? Correct? Which would mean my dy would be x squared dx. Mathematically, theoretically is what they called it on there. They said, we don't have a theoretical, do you remember her saying that word? We can only do it numerically. This can be done both, and I want to show you how close they are. That's why I'm doing it both ways. So when I integrate, I get y would be x cubed over 3 plus c. And it was it 1, 0, or 0, 1? What was my initial? 0, 1. Yeah, when I put in a 0 for x, a 1 has to come out. So what's c? Yeah, a mathematician, if they had that rate of change, they're never doing this stuff, right? Because this is separable. Boom. Now let's go check it out. Go take out your calculators now, because I don't want to do this part right here. And I want you to do our y of 9, the actual value, sorry, 0.9, will actually be equal to, scratch the approximation, exactly 0.9 cubed over 3 plus 1. Keep in mind, too, guys, we were only taking 3 steps, correct? And we're going from 0 to 1 in 3 big chunks. Does that make sense? And watch how accurate our numerical approximation actually is. It's 1 point something. 1.243. All right. So when I go up here and take my actual value that we wouldn't have if we were using this method, it's just go subtract them, and I'm accurate. What did I get? Point what? 108. That's pretty accurate. I'm only like a tenth off, and I only took 3 steps. Does that make sense? So now watch. We'll do this. And then I'm going to show you how it appears on the AP exam. So I want you guys to run through this guy right here at the bottom. My y prime is twice x. I want you to start at 2, 5. We need an initial condition. And you're going to use 2 steps. And you're going to estimate 2.4. Try not to look at your notes. Try to have that table like, what am I doing? I'm hopping on. I need a slope. Then I'm going to take a step left or right, a step up or down, and be at a new point, and then wash, rinse, and repeat. The table method is super easy to remember, because visually think about what you're doing on the curve. Hopping on, sloping it out, walking, new point. And then I'll ask you guys to fill in the missing pieces of my table. So 1, 2, 5. Then my y prime. Gonna walk over, walk up. You got some new spot. Boom, boom. Notice how I was using words. Whoop. Delta x. Need to get from 2 to 2.4 in 2 steps. That's all I'm going to do. Isabel, do you think you should even need to memorize that table? Not really. You just walk into typo. And then every once in a while you're going to stop and readjust. Walk it in. Watch your arithmetic. Yes, I could do that. That's my answer. Actually, there are some freebies. There's more freebies here than I think. I put in all the stuff you don't have to think about. Now wait till pencils stop moving. Mosey on to how it appeared. It's not hard, is it? It's kind of leisurely. I mean, your worksheet has some higher level questions on it, so you're going to have to be careful, but Euler's itself is easy. Go ahead and help me with my missing pieces. What's my first slope or my first tightrope going to be set at? 4. Okay? But then I'm going to move over. I'm going to move up. How far up? 0.8. 4 times 2 is 8. There's 1 decimal place. 0.8. I will get to 2.2, comma, 5.8. Correct? Now I'm going to hop at that point and I'm going to readjust my slope. Okay? So now my new y prime is 4.4, twice my new x value. I still am going 2 tenths to the right, and then multiply those, I get 88, but 0.88, because there's 2 decimal places. All right, what do I add that to? My old y, and what do you get? 6.68. How many of you had that? X. That's it. That's Euler's method. Keep in mind, we're not out in space with ugly numbers and values, but this is the process for it, right? What does 6.68 represent? It means that my approximation for where I am on that function, and usually input is time, but we're keeping it all y's and x's, is 6.68. Do you think that's pretty accurate or not really? I'm going to say it's probably okay, but I took 2 big steps, correct? I mean, the more iterations you do, meaning the smaller your step size. So now what I want you guys to do is, I'm not going to do that one at the top there. I took some off of past AP exams, and I'm going to demonstrate how it appears multiple choice, and then how it appears FRQ. So you guys go do this one and the first one, and then they also sometimes have it tabularly. So go ahead and, again, try not to look at it. Make your table by using common sense. I need to start. I need to walk. Then I need to move over, up, new point, repeat. Your table falls out really nice. Be careful with arithmetic and don't touch your calculator. 9 would have been not calculator active. You're my only class of this, and I haven't done it since last year, so I do not know the answer, and I hope you guys agree, so I don't have to. What's your step size? Positive, yep. They're not always positive, though, so always watch whether you're going backwards or forwards in the curve. What'd you get, Joel?
3.
Do you have any backers on a 3? Okay. If you didn't get a 3, can I ask you to consult with the neighbor when we're done? Right? It'll make us go faster. All right? Do we, for the majority, agree on a 3? I don't see people going, well, where did the 3 come from? I saw one person. John, do you get a 3? Okay. So you had a question mark in your eye, so I was like, all right. Now what I want to do is we'll do the table one together, so let me see if I can scroll. When I'm recording, it's hard to scroll. All right, so this was a number 83. I don't know why it says 83. Oh, I do know why. All right, so let's go take a look at this guy. It says the table above is values of f prime, blah, 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 Euler's method. The minute you see that, you hop on that curve and you start making a table. Regardless of how it's presented, you're going to ask, where am I starting? How am I supposed to slope it out? That would be f prime in this scenario. I need to figure out how far do I move over, how far do I move up, and then I'll be at my new point, and then you go start filling it in. The table's super nice. So where is this one starting? At 1, 4. Now I gotta figure out, I want to figure out my step size next. I need to go forward. Oh, it tells me my step size. Thank you, College Board. They're nicer than I am. All right, so 0.5. All right, let's go ahead and start. What is my first slope that I'm going to walk? 0.2. It says on the table, f prime of 1 would be 0.2. Over here, my delta y is the product of my slope and delta x. It's a slope formula. What do I get when I multiply those? 10, but, so what? 0.10. All right, my new point. How far did I move to the right? A half. How far did I move up from 4? 0.1. What am I supposed to estimate? F of 2. I got to go another one, correct? So 1.5, comma, 4.1. Now, what's my new slope? I don't even have to calculate it. What's my new slope? I love tabular when College Board does this. They just want to know that you can talk the method. It's kind of nice, right? Where did my 0.5 come from, just in case? The derivative at 1.5, correct? I'm a consistent step size. Now be careful whether this is 2.5 0.25, 0.025, what is it? 0.25, correct? My new point, I'll be at 2, and then 4.35. What do you think? Nice and easy peasy, it makes sense. Now I'll show you FRQ, alright? This is actually 2010's actual number 5. Alright? Not all of these points went towards this, so your points get split between a BC score and an AB subscore. And I've told you that. So your FRQs are sometimes a crossover. Actually, 3 of them are identical to ABs. Your other ones, sometimes they insert pieces. So for example, on this one, it does give me a Diffie Q. So I'm like, okay, they're giving me the differential equation. They're giving me an initial condition. So I'm thinking, okay, they're going to have me figure out what's going on in the actual function. Not quite sure what this is in there for because I haven't done it since last year. So I'm not quite sure why they're telling me f of x is less than 1. It must be for a reason as I work. Now, do you think part A is going towards your BC score or your AB subscore? Go do it. That would not be on the AB. AB might have the other 2 questions, though, with something else. They would probably have, like, write a tangent line equation or something. So bits and pieces of your exams are identical. And then when I'm done with this one, we are done. I'm doing Eulers in a day. This class. But I won't collect the homework till Monday. What's tomorrow? Do you remember what I told you is tomorrow? Do you remember? AP classroom quiz. Yeah. It's on separation of variables, slope fields, and Eulers. Be careful on this one. Why did I say be careful? Did any of you notice? Yeah, you're going backwards, so what's your step says? Negative. Yeah, you're going from 1 back to 0 to approximate, and it says 2 steps. So you have to get from 1 to 0 in 2 steps. Your step size is negative 0.5, so be careful with that. Where's my point? Oh, there it is. 1, 0. I'm just letting you try these on your own so I don't have to do a ton of them. Is your first new point 0.5, negative 0.5? Yes? I get sloppy with these myself, actually. I get impatient. They're easy though, so it's nice. What's my new derivative? 1 minus my y value? What's my new derivative? 1.5. Still walking. You have to multiply 15 times 5 without a calculator and then move the decimal place twice. Where do you get?
-0.75.
Thank you. Negative 0.75. So now you would be back at 0 and a negative what? Yes. So you have to do negative 0.5 minus, right? So where are you? We're not agreeing. Where are we? Say negative 1.25. Okay? Or you could keep them as fractions and use a negative 5/4 if you did that. It kind of just depends on you whether you like. If you wanted to deal with halvesies, 3/4 if you like fractions better, you can. Now read this one and kind of decide what skill it is. FRQs are deadly because they mix. You never know what's coming next. Yeah, I started with Eulers, but part B, what calculus topic is part B? Yes, it's a limit, but it's L'Hopital. Because what happens on your direct substitution? Now, do you remember how I told you have to write it when you're doing L'Hopitals? If you want full points, what do you have to tell me? Limit as x approaches 1 of f of x, which would be f of 1, which is limit x approaches 1 of the denominator would be 1 kilo minus 1, which is also 0. Now you can do L'Hopital's to get full credit. This would be 2 points. Okay? It actually went 225 on the scoring guidelines. So now when you do L'Hopital's, you're going to go x approaches 1 of f prime of x all over what? 3x squared. So now I have to figure out what dy dx is. So they're testing that you understand that f prime and dy dx are exactly the same, correct? I have to do 1 minus the y value when x is 0. Right? So when x is 1, when x is 1, what's the y value? 0. So what's the slope there? 1. So a 1 on the top and a 1 on the bottom. 3. Correct?
That's okay.
Are we good? That was weird, right? It went Eulers and then psych, L'Hopital. Now, again, you have to know what this is asking. I know you know how to do it. But again, you have to know what skill do I launch into. You've been taught all the skills. You have to know which one it is. Eulers, it flat out told you. This launched into L'Hopital's. What is this? This is that's separation of variables prompt. Find the actual solution to. I want what y equals. I'm not going to have you do that because that's what we've done the last 2 days. But that would have been a 5-point separation of variables. Are we good? All right, so I'm going to give you worksheet number 2. Technically, it's due tomorrow, but we're not moving on until Monday. So if you would like to save it, if you have a busy night tonight or something, yeah.
You said the College Board doesn't accept like charts and sign lines and stuff.
They
or
don't look at it.
Does
that's
does it
sign
count
lines.
for-
That counts for your work. Yeah, you get full credit for that. It's a pretty common way of teaching it. The other way looks hard, but it's not. We should actually try one with the other way. Maybe you'd like it better.
Everybody knows how I do.
All right, I'm gonna pause this. If you're watching the video, we're doing worksheet